sensors. So what's a pressure?
Force.
No.
Oh, so what's pressure? Because no pressure. Right.
It's kind of like, huh?
Are you gonna pull it on?
Yeah. Sorry.
Is it like how much bearing, I mean, how much they're pushing on each other around?
Basically, it's just a difference in potential, right? So all pressure is just so we can't have, and it's kind of like speed. You can't have speed without motion. So they're so entwined with each other. So you can't have force without a pressure, but you can't have pressure without pressure creates force. Does that make sense? And most people get these things confused with each other because they're so closely related to each other. So we know what a sensor is by now, right?
No,
We don't.
probably need to go over that.
And these are some of the things we came up at the start of the semester that we talked about. And what's in red's the ones that we've already talked about, and the one in green is the one that we are going to talk about now. Like I said, we're not going to go through all of these. There's just not enough time in the semester, but we're going to look at pressure, and then the next thing we'll look at is flow, and maybe get some time to look at how we can sense orientation and the shape. So basically, pressure is a difference in potential that's applied perpendicular to some surface of an object per unit area. So one thing we got to do is we got to understand area. Another thing we have to understand, and I don't have my headset, so I need to stay back over here. Another thing that we need to understand is that is the different scales that we have to learn, especially around here where we're at now, where we've got companies from different countries that actually use different units. So force. So like we said, we can't have force without a pressure. So basically, even all our pressure indicators, we're going to have a unit that takes pressure and converts it into force. So technically, what we're actually measuring is a force. And then we turn around and use that to calculate the pressure when we actually see the formula. And some of y'all might have already known it, especially those that had the fluid power course, the hydraulics and pneumatics course.
What's the formula for a force sensor? Force.
Force, we'll get that. Y'all don't know it yet. It's in here. We'll get there. And huh?
It's torque times length. Right?
No, that's work.
Okay.
Yeah, force is area times pressure.
Okay.
So how much area the pressure is pushing against. Yeah.
I'm still here. Let me finish.
An interaction that when unopposed will change the motion of an object. So it can have pressure without force. So if I come up here and I push up against that wall, right, you understand, I'm not generating a force. So force, we have to have what? We have to have motion, right? But we can't have motion without pressure, which is pretty good. The push or pull on an object with mass that causes it to change velocity or to accelerate. Now, force sensor, the transducer that converts an input mechanical force into electrical sensor, but I should have put the pressure sensor up here. So what we have, basically a pressure sensor is, first of all, we generate a force, and then we measure the amount of displacement of that force, and then we use that to calculate how much pressure that is. So just about all your pressure sensors actually have to generate a force to measure pressure. So here's the formula, a little math, a very simple formula. So force is equal to area times pressure. So if I can measure the force, so what would the formula be to calculate pressure? So we can use our little wheel that we learned back in DC, right? So force is equal to area times pressure. So pressure would be equal force divided by the area. So we could come up with the force that's caused that pressure. I mean, the pressure that caused that force, right? All we need to know is what? Measure the force and then the amount of area that it's displacing, and we can calculate the pressure from that. Are we okay? So some terms. Pressure, 1 atmosphere. Everybody okay on atmosphere?
Yeah, 14.
Yeah, but where's that at?
14 sea level.
And it's not even at sea level. It's the average for sea level, because we have high pressure and low pressure, right? You're moving around. And even at sea level, this could change. If you got a low pressure area sitting over the sea, then what? It's going to be at a lower than 14.7. If you got a high pressure area sitting over there, it could actually be a little higher than that. So this is the average pressure, basically, of what we would have at sea level. Another unit that we use is something called pascals. And a pascal is a very, very small unit. And we got a conversion chart up here. That's something I should know. So if we were measuring sea level using pascals or atmospheric pressure at sea level, then it would actually be 101.3 kilopascals. So pascals is a very small unit. Or we can also represent that in torrs. I don't know if that are bars. Bars is used a lot because it's a little better unit. So 1.1 bar would be the same as 101.3 kilopascals, which would be the same as 14.7 psi. So what we have to do on a pressure sensor is basically this. We have to have multiple parts, and part 1 would do what for us?
Converted pressure to force.
Yeah, so it's going to do a displacement, right, for us. And then part 2, we're going to have to do what? Yeah, we're going to have, so it's going to be multiple transducers. So one transducer is going to take it and convert it into a displacement. Then the next transducer is going to measure the displacement and convert it into a electrical signal. So what is a transducer?
Converts something, well,
Converts one form of energy into another form of energy. So technically, the engine in your car is a transducer, right? So we have a lot of things that are transducers. So this is basically the makeup, and this is almost true on all sensors, because even though we have like thermistors, a thermistor changes its resistance. Changes its resistance with temperature. But the problem is we cannot process resistance, right? We have to process either voltage or current. So then we got to have some other transducer that converts what? Resistance into voltage. Now, for most sensors, it's pretty simple. We just add a fixed resistor. Or if we want to set a zero reference, then we put it inside what we call a Wheatstone bridge, right? Okay. So here's our different pressures that your gauge is going to measure. We have what we call absolute pressure. This is relative to a perfect vacuum. We have gauge pressure. This is relative to atmospheric pressure. You can tell, and most of our gauges measure gauge pressure, and this is why it's got the name. So if you've got a pressure gauge and you look at it and it's setting at 0, that's pressure gauge, right? You understand? If you had absolute pressure, then that pressure gauge would be set at about 14.7 psi at sea level. So you can tell right off the bat what kind you got. So most of them most of the gauges that you'll run into is a gauge pressure, because that's basically a lot to deal with the work that you're getting. Because your pressure is the actual atmospheric pressure is actually pushing against whatever you're trying to move, right? Does that make sense? So gauge pressure is showing you basically the work that you're going to really get. Vacuum pressure, this is any pressure below atmospheric pressure. So anything below 14.7 psi is considered to be a vacuum. Are we okay?
Oh, you said anything under what? 14.7?
Anything above sea level is considered to be a vacuum.
You said above 2?
No, above. Any pressure above, and what am I saying? Any pressure below, so I am saying it wrong. Any pressure below 14, I said it right the first time though. Any pressure below 14.7 psi is considered to be a watt. Vacuum, thank you. Differential pressure, we use these a lot. Differential pressure is just a difference between two pressures, right? And then sealed pressure, this is going to be a pressure that would be relative to some pressure that your company is set. Everybody okay? That makes sense? All these make sense? And all these are up on Blackboard, right? Now we measure pressure in either pounds per square inch, or we measure it in inches of mercury. What's that?
Yeah, nobody do that.
Does what?
Measures pressure in inches of mercury.
Oh my goodness, y'all wrong. You were totally, nobody does that.
Okay.
Nobody does that.
No.
No one. So when I go to the doctor and he or she takes my blood pressure, or when they give out these pressures on at night when they're saying we're having low pressure or high pressure.
Set in our
No, that's not what you said. What did you say? Nobody. Then we have inches of water. And of course, we know about pascals. These are going to be measured in newtons or bars, and also torrs. I don't know what's that. Why that's not in there.
You know, Pascal.
Well, we know what pascal is. Do you? And then kilograms per centimeter square. Everybody okay? U.S. customary. So what do they use out at Brother? Do they use both of them? A lot of companies, bars, yeah. But a lot of companies that over here, all the pressure gauge will actually have 2 units on them. They'll have the U.S. customary, and then they'll also have some of the industry standards. I mean, some of the ISO standards.
We're all
Yeah, bars. So y'all go to the bar. Right?
Yeah.
The pressure resulting from a force of 1 pound force applied to an area of 1 square inch. So this is what we use a lot over here, PSI. And what does PSI stand for? Pounds per square inch. And of course, we've already looked at force, and we looked at the formula too, but here's the formula. So most of your sensors that display pressure somehow convert a force over to a pressure, right? Either mechanically or electronically. So basically, this is the way inches of mercury done. Most of the time, it's done with electronics now. The pressure exerted on a circular column of mercury of 1 inch in height at 32 degrees Fahrenheit. Y'all might need to know this, right? Or water at 39 degrees Fahrenheit at a standard acceleration of gravity. So basically, they come up here and place a pressure, and then it displaces mercury. They know the weight of mercury, and they know how much area they have. And of course, when it generates that force, what's it going to do? It's going to come up here and move it up, and then we measure it on the other side. And this is technically the way they came up originally. Whether anybody still uses this, I'm not sure. Most of it's done electronically now. Most of it's, now I'm not saying inches of mercury.
I know what you're saying.
I'm saying this is not the way it's usually measured now.
Yeah.
Pascals. This is the international standard, or what we call the SI standard for pressure. So basically, we and maybe 2 other countries are still using PSI. So most of the companies you go to work with, especially international companies, are probably going to use pascals. And then, of course, what they're going to do is, since pascals is such a small unit, usually they'll use a bar. So a bar is just another representation of a pascal. So 1 bar would actually equal to what?
14.7 PSI.
No, 1 bar would actually equal to what? We're good. We're going pascals. So it's equal to 100,000 pascals, yeah. So bars are a lot easier to deal with than the kilopascals, right? So the kilopascals, of course, we do the same thing that we do. We just move the, if we had the number of pascals, we would just move it to which way? We start moving it to the right, 3 points, and we call that kilopascal. Now, 1 kilopascal, this is it, so there it is. So 1 kilopascal is actually 1.45 psi. So Pascal is an extremely small unit. And so, and when we see it, we're going to see kilopascals, right? You understand that? Or bars. And this is a chart that a Newton. We use this. Normally, I don't usually see newtons in measuring pressure. Where do you usually see newtons at? Huh?
We use those at work.
Yeah, but
UTM testing
yeah.
on the where they pull the components we welded apart, and then we get a measurement of how strong the welds are,
Okay.
and when they break.
Usually we use a lot to measure torque, though. A lot of your torque wrenches are laid off in what? Newtons, which would be basically what y'all measuring it too. It's not really a torque. A torque is a turning thing. And that's where I see newtons most often used, but that would be, but now that you think about it, these are strength detectors, right? We use literally break them to see. Break them or squish them. We used to have a metallurgy program here at the college. You know, they had one of those machines here where you could, and I don't remember what the unit on that machine was, but it was fun to play around with anyway. This is the conversion chart. This is a pretty interesting chart where all the different units that you might run into, no matter what they are. And of course, you can get this off the internet, but you also can just get it off of this Blackboard slide right here. Don't really know where I got this from. I should have gave credit for it, but I got this off the internet somewhere. So we could go from bars to, 1 bar would equal to, this would be equal to 1 PSI, right? That makes sense. So it's a pretty interesting chart. Now all these math formulas, of course, here, you're not going, it won't be on the test, but this kind of stuff right here will be, right? You understand? So these are just different pressure gauges, and these are dial indicators. More and more we're going to digital indicators. And a lot of these are actually being displayed up on the HMI panel. A lot of them have, so this one is in the kilograms per centimeter squared, the one on the bottom right. This one is in what? I can't say this.
40 inches.
This is in inches of water. Now this is in PSI, and this was in bars, which is, I say, this was a long time ago. Can y'all see the fluid in here? It's actually a type of oil. You know what that's in there for? First time we ever saw it, we thought the gauge was bad. This was years ago. And, we said, this thing is leaking and it's getting the fluid up into the thing.
Yeah, why do you?
It's in there to dampen the needle. Because a lot of times when you deal with pressures, the pressure is constantly varying. And what would happen is the needle would sit there and vibrate a lot, and eventually it would tear up the mechanics of the thing. So it's in there just to dampen the needle, to keep it from what? From bouncing around. Yeah. Anybody that's got a compressor at their house that don't use one of these could actually see the needle jumping around a lot. And I've had to replace mine at least once.
Yeah, I had one for the car tire.
Yeah, just finally.
The pressure gauge, and it just like moved up with the dial, like over high, turning the dial.
This is inches of mercury. This is a pressure cuff. Anybody that's ever been to the doctor, you dealt with. This is millimeters of mercury. It's usually what this thing measures at. I thought that was interesting. So I knew Kurt was going to be in my class and bring that up. And of course, weather. This is what they measure pressure, atmospheric pressure at when they give you low pressure and high pressure. Sometimes James Spann actually says. So basically, these are the different types of elements that we're going to sense a pressure, but actually they're going to generate a force, right? You understand? So most of our pressure sensors actually generate a force, which gives us a displacement, and we can measure the displacement, and we know then we can use that to display. So bourdon tube, helical bourdon tubes, flat diaphragms, and we do have some of these. Convoluted diaphragms, capsules, and bellows. I think we got a bellows, we got a bourdon tube. We don't have a helical bourdon tube, and we do have a diaphragm that I can show you. Transducers, these are the devices that we're going to use to convert a displacement into a pressure. Potentiometer, piezo-resistive device, piezoelectric, inductive, capacitive, and also solid state. I need to add that on. Okay? So the term piezo usually means a pressure. So piezo-resistive means these guys are going to change their resistance with a pressure, which technically is still a force, right? Piezoelectric, these are interesting devices. Piezoelectric crystals only detect a change in pressure. So what would, and we'll see these. Inductive LVTs we've already looked at back when we did these. These things give us a voltage that's proportional, but it also gives us a phase shift depending on the direction, right? Did we talk about those? And of course, capacitive. So these are our bourdon tubes. And, if you've ever played with a little party whistle that y'all used to have when you was at parties, when you blow on it and it unrolls, that's a bourdon tube. So these guys, they are either solid metal. So this is the pressure gauge right here. And this is the actual bourdon tube around here. And then, of course, we bring the pressure down at the bottom. So what happens when the pressure comes into a bourdon tube, a helical bourdon tube, it would try to make it come out of the helix, unwind. A bourdon tube, by the way, these things can measure both pressure and vacuum. So if we put a pressure on it, what it's going to do is it's going to cause the bourdon tube to try to come out of that sea that it's in. If we put a vacuum in it, it would cause it to try to contract, right? That makes sense. So we can use bourdon tubes to measure either a pressure or a positive pressure or a negative pressure, which would be a vacuum. Everybody okay? They are, and they're very, of course, this is solid metal, so this guy here would handle a lot of pressure. Now, this used to have a mercury switch right here. So this used a mercury switch, so this would give us a digital output. And what you'd do is you'd set the amount of torque you put on the bourdon tube, and then we could set what we call a span. And what's a span? A range where we could set a low pressure and a high pressure range. Here you go. These guys are very, and of course what we would do if we wanted to go to electronics, some way we would measure the displacement. So this is the example is using an LVDT. So an LVDT, remember it works off AC. Y'all remember that? Yes or no? Yes. And what it does is it gives us out it sums two of them together. So it gives us out one, and then the phase relationship would tell us the direction. So we could use this to measure a vacuum or a pressure, right? And then, of course, the amplitude tells us the quantity. Now, the helical one is going to try to do what? It's going to either try to come out of the twist, or it's going to either twist more depending on the direction of the pressure. We're okay? So we're taking an LVDT, which is technically a position sensor. And then we bring in pressure or vacuum. This is going to, we bring in a pressure, this is going to try to cause it to come out of the C, right? It's going to try to open it up. And then the LVT would give us, it would convert a pressure into a voltage, right? First of all, we take a pressure, convert it to a force. Then we take the force and convert it, the displacement created by the force, and convert it into a. So this is basically what we have there. These guys are very, very rugged. They, this is the one that we have. I might have got these. I just added this today. This is the one that we have. And this is electronic. We'll look and see basically how this thing probably measures pressure. So this guy's showing 0 right now. So what does that mean? That means this guy is gauge pressure, right? So just about any pressure gauge that sets at 0, this is gauge pressure. So what it's done, it's subtracted out the 14.7 psi that's acting on it right now. And of course, it's programmable. What's neat about this one, it provides not only a digital output, it also supplies an analog output. So a digital output, we can set it up to measure a span for us, which means we can set it up to give us a low and high range, or we can set it up just to measure pressure. And it's programmable. And it also can measure a vacuum. I don't remember how low it is, but it measures vacuums, or it measures pressures. So, are we okay? By the way, this operates off 24 volts. So what we do is we have an interface. So an interface is a go-between, right? It's connection to. And this is the term that the discussion section on these different sensors uses quite often, what an interface is. So an interface means we make a connection to. So what we're doing is we're taking a 24 volt sensor, and then we're running it through 2 relays, because this is a 4-wire sensor. Actually, it's got 5 wires. And what would the 5th wire be? So the 5th wire would actually be the analog output, right? So this guy will give us a output voltage that would be proportional to the temperature, and we can look at it and see what that is for our transfer function. Then it's got 2 other wires, so it's got a white and so it's got white and black. So it means it's got 2 contacts if we use it as a digital sensor. The white one would be the normally closed, right? And then the black one would be the normally open. Everybody okay? Blue would be what? Negative, right? Or if it's AC, it would be L2 or con. And then the brown would be what? Positive for DC, or it'd be L1 toward And then they're bringing these over to 2 relays. So we'd have to figure out which one works for the normally closed. And then the relays that they have, these are all single pole double throw. So we have a normally closed off this one and a normally closed off that, normally open, normally closed here. And then we would have to figure out which one we want to use. And it's pretty obvious when we look down at the bottom which one. So it's got C, what would that be? Common. And then this would be the normally open, normally closed for this relay. And then this right here, C, this would be the normally open and normally closed for this one. This is the counter EMF diode. We talk about that? Huh? The problem we have with DC coils, what's required to induce a voltage? Okay. That's one thing. Number one would be a what? So when I have a relay coil, we put a current through this and we generate a magnetic field. And so basically a solenoid. Then we use the motion of the magnetic field to close contacts, right? Then 2, we got to have what? Conductor. And then 3, we got to have what? Motion. So I've got this now on a DC relay. The only way it gets its resistance is through the gauge of the wire or the size of the wire. And then, of course, the number of loops. And what determines the resistance of a wire?
Material. The size.
Oh, I got it. I ain't say tolerance this time, me.
Yeah.
I can't say it all day yesterday.
More than one. Temperature. So what happens on a DC coil, we've got a lot of turns of fine gauge wire because that's the only R that we got, right? You understand? And I'm coming over here and putting plus and minus. And how much resistance does wire have? Well, don't have very much, right? Unless we have a lot of what? If we have a lot of what? Length and a small size. So what happens when I come over here and put a voltage across this thing and current goes fluid, it builds out a magnetic field. Now what happens when I turn that thing off? Well, this magnetic field comes collapsing back. And all of a sudden I've got a magnetic field, I've got a conductor, and what determines the amount? Strength of the field, right? Yeah, this is what gets us on these things. The number of conductor loops. And 2 would be the speed of the motion. So the problem we have with DC coils, DC relays, or even DC solenoids, is that when you turn this thing off, this magnetic field comes collapsing back into that, and we got a lot of turns of wire, and it induces a high voltage back into that thing. Now, there's not much current available to it, but the voltage is so high, there's one of the ratings on all electronic devices, it's called the breakover voltage. If you exceed the breakover voltage of a solid state device, it will be damaged. Now, the problem is it built out this way. So when it collapses back, it generates what we call a counter EMF. So this counter EMF, and over on the other classroom, in one of the other classes, you need to let me demonstrate this to you. We have a neon light bulb that we come up and we put it across a DC source, and it takes over 90 volts to turn it on, to make it glow. We come up here and we take that neon light bulb and we put it across this thing, and we charge this up to 12 volts, And then when we turn that thing off, that light bulb comes on, which means that counter EMF that was generated was over 90 volts. Even though I charged it up with what? 12. So what we do on anytime we have these DC coils, we put a diode opposite of the polarity of the applied voltage. So that means we'd come in and we would put the diode like that. Now, a diode is a check valve in electronics. A diode would only let current flow in one direction. And to get it to flow, we would put the minus up here and the plus down here. Well, when we come up here and put power on it, then the minus is on the top and the plus is on the bottom. And this thing right here is a check valve. It's what? It's turned off. But when we discharge this thing collapses back in there. This goes minus, this goes plus. The check valve opens and shorts out the counter EMF. And it's not much. It's not current. There's no current available because one, this guy here has a lot of resistance, so it's discharging through the resistor, right? You understand that? And then plus, there's just no current available. So what this counter EMF diode in there, some people call it a flyback diode, is to prevent this thing. When you turn off that coil, it's in there to prevent that counter EMF from damaging my pressure sensor. So don't take those out and make sure you put them in there in the right direction, right? So we had a big printer that we was working on that had a bunch of solenoids in it, and one of the transistors that fired the solenoid went out. We replaced the transistor because it was bad, but guess what? We didn't check. We checked that thing. And we fired this thing back up. I don't remember how much that big printer cost. It was a 600 line printer, so it could print 132 character lines, 600 lines every minute. So these guys was flying. We had one that this might have been the 2400 line printer. And when we turned it back on, the transistor caught on fire. We was down on our knees trying to blow out the fire inside these circuit boards. It's funny. You already got to laugh at it over there. So these are the counter EMF diodes there. And so, and you'll see these. Any solenoid that's operated off electronic devices, you'll see these guys right here. Can y'all see them? The little bar, so one end's white, that would be the negative side, and then this would be the positive side of this side. And so if y'all go over and look at the Amatro lines and stuff like that, when we go over there and let y'all try to find all these sensors, every one of these relays, coils, you'll see a watt across it, a diode. This is kind of like the one we're passing around. This is a diaphragm type. Here you go, Kevin. You need to get off your phone, man. Don't need to get off y'all's phone. I prefer y'all not to even have y'all's phones out while you're in my class. We're having problems with people doing that. Which is in the course syllabus, by the way. And it's a college-wide policy. So this is a diaphragm that we're passing around. So basically, this just has a plate inside of it, and it's sealed. It's got a belt. It's got a unit over here, and then it's inside a sealed unit. And all you're doing is what? Got a hole. You push it in there. It's got a spring that causes it to do what? Either displace. This brings a rod out the back, and then whatever we're going to transfer it over to, take a linear motion and convert it over to a voltage, or be attached to the rod. A very simple sensor. But this is just the sensing element, right, that we're passing around. We have to take the sensing element and run it through another transducer to take a displacement and convert it into electrical signal, right? This is a bellows. This one on the left will measure differential pressure. Can y'all see how it works? So we bring one pressure into the bellows, we bring the other pressure into another input, and then this guy would measure actually, this displacement would measure the difference in pressure, the one we're going to pass around. So this is the bellows type. Whose turn is it? So this guy can measure a vacuum, and it could also measure a pressure. So a pressure would cause it to do what? Expand. A vacuum would cause it to contract. And this is just the sensing element. We'd have to combine that with something, right? You understand? To get an electronic sensor. So this is an example of a bellows. I don't know what they're using to measure it, but whatever it is actually over here. Whatever units inside that would be whatever's in there. We could put it on a rack and pinion and have it turn a potentiometer. We could use an LVT. We could use several different sensors to turn this around. Right? This is a capsule. This works almost identical to a diaphragm. These are basically two discs that are made out of a metal. They have the ridges in them, and they're sandwiched together. So when we put a pressure on it, they're going to cause them to do what? Expand out. We okay? Yes?
Yes.
Solid state pressure sensors. These are very, very popular now. For years, and we always used mechanical. What's nice about a solid state sensor is a solid state sensor is going to vary something that's already in electrical, right? It can either provide us a voltage or it can provide us a resistance. We have a piezo electric that produces a voltage when compressed or expanded. Piezo-resistive is a sensor that can change a resistance with the pressure. And these would both be considered solid state. Now, the difference between a piezoelectric and a piezo-resistive, a piezoelectric, it only detects when a pressure changes. A piezo-resistive would actually change its resistance with the pressure. Everybody understand that? So piezoelectric quartz crystals produce a difference of potential only when they are compressed or only when they are expanded. So we don't use these as static pressure systems.
See those.
Huh?
See those.
Yeah. But they only give us what? They only indicate a what? A change in pressure, right? Piezoelectric, anybody ever played around with one of these? Anybody had one of these striker lighters where you hear a snap?
Yeah.
That's piezoelectric right there. So what you're doing is you're snapping a quartz crystal, and it generates a voltage that's high enough to arc, but then it's what? Then it's gone. Even though you're still holding down on your switch, it's still gone. Right? You understand? So that's piezoelectric right there. So just about everybody in here has seen one of those. Well, we could do the same thing, but notice this guy here is only going to give us what? It's only going to give us a difference in potential when what? We can use it to check turbulence, blast, ballistics, like the speed of a bullet or something like that, and of course engine combustion when the engine combusts. Are we okay? No?
Yes.
So this is just a piezoelectric example of a piezoelectric crystal. I mean a piezoelectric. So we'd have to have something that actually senses the change in pressure, then it would cause a motion. The motion would cause the piezoelectric to either compress or expand. This would generate a voltage. Then we would try to modify it to whatever we need, right? This makes sense? This is probably becoming one of the most popular pressure sensors. These are piezo resistors. These guys operate very similar to a strain gauge. Silicon changes its resistance when stretched or compressed. So we usually run these in groups of 4, so then we get the average of it. We have basically a diaphragm that the silicon strain gauges are connected to. And then when this thing comes in, it warps the diaphragm. It changes the resistance of the silicon strain gauges, which gives us, we connect this to a voltage, and it would give us a voltage that's proportional to displacement, which would give us a pressure indication. So these work very similar to the strain gauges that we talked about in our force sensors, right? I uploaded a lot of them last night, but I don't know if it's the last one that we got. It's probably not up there yet. So guys, that's about it on this. Any questions? Anything we need to go back over?
No, we got that, dude.
We're probably going to try to finish up our lectures today. We only got one more. And then when we come back after break, we'll be in lab. So, we'll be in lab the whole class. So that sounds like a winner. Okay, guys, y'all go ahead and take a break. 10 minutes. So I think I've got